My name is Pells and I'm presenting here on behalf of the Southern Highlands Coal Action Group the results of a study of the likely groundwater impacts of the proposed Hume Coal project at Sutton Forest. The groundwater study was undertaken in September 2013. But before I go on to the study, I wish to refer first to a report done by what is now the New South Wales Office of Water in 2004. That is titled A Review of the Status of the Groundwater Resources in the Southern Highlands, New South Wales. That study considered in detail the parishes that encompass the Hume Coal project, primarily Bong Bong and Sutton Forest. The study looked at each parish in detail and, as shown here for Bong Bong, analysed all the available water bores in the area to assess the groundwater resources of the Hawkesbury sandstone. The study concluded that the groundwater resource that underlies much of the Southern Highlands is highly valued for its good quality and high-yielding supplies. It went on to note, however, that existing groundwater entitlements in Bong Bong and Sutton Forest areas exceed the calculated sustainable yields, but noted that there was no groundwater model and that one should be developed as a matter of importance. In particular, the study noted that the present situation, that's in 2004, in what has long been recognised as an at-risk system, necessitates intervention to ensure resource sustainability and environmental protection of groundwater-dependent ecosystems. We have prepared a groundwater model of the kind recommended by the New South Wales Office of Water. This model has been independently reviewed by the Water Research Laboratory of the University of New South Wales. In this presentation, I will first explain the development of the model from the rich database of information available in the area. I'll then summarise the key computations, summarise precedents at Berry-Macquarie, and draw the key conclusions. The groundwater model area is much larger than the exploration area, which is some 89 square kilometres defined by Authorisation 349. The exploration area is encompassed by the ground model area shown by the blue lines in this plan, and the boundaries of the ground model area have been chosen along rivers or near dams so as to be well defined by surface water conditions. The northern groundwater boundary runs along the Wingecarribee River from almost the western to the eastern sides of the model. The southern boundary runs along what is known as the Grand Canyon, being Bundanoon Creek, and once again this is a very well defined topographic and groundwater control system. Our first task was to create a digital model of the terrain, which is a computer-based model that shows all the creeks, the topography, and all other surface features that are relevant to the groundwater modelling. We can zoom in on this digital terrain model and see the Hume exploration area and the location of Moss Vale. It should be noted that the terrain covered by our model includes two catchment areas. The orange catchment area feeds into the Sydney water supply and the blue to the Shoalhaven. The groundwater model encompasses both catchments, although the mine will fall mainly in the Sydney catchment. Geological information was taken from published plans, and this one here shows the geology of the area with the olive material being the overlying shales and the light green material being the Hawkesbury sandstone, which is the dominant groundwater system in the area. The orange blotches on this plan are volcanic intrusions, and outcrops that occur in the area. You can see in the cross-section below the gently dipping coal seam that dips down towards Kangaroo Valley in the east. Unique to this area, the Hawkesbury sandstone sits directly on the coal seam. This is shown by this Hume model of the geology, where you can see the Hawkesbury sandstone directly on top of the nominally 12 metre thick Wongawilli coal seam, of which only about 3 to 4 metres is productive coal. We have analysed the logs of more than 250 boreholes and shown that in 90% of the cases the Hawkesbury sandstone is in direct contact with the coal. This means there are no meaningful aquicludes between the coal and the Hawkesbury sandstone groundwater system. Our next task was to assess the contours of the coal seam, because all the overlying strata follow the contours of the coal seam, and therefore these contours provide the basis of our stratigraphic model. As we zoom in on these contacts, we can zoom in onto the area which is most likely to be the target for the Hume mine, and we can see that that is the case by comparison with where Hume coal are proposing their phase 3 boreholes. These are closely spaced boreholes just to the southwest of Golden Vale Road. We then obtained water level data for the many boreholes in the area, and there are very many of these which can be seen in the red dots in this plan, which again we can zoom into the area of the probable coal mine. This water level data was the basis of our calibrating our model in terms of present day conditions. We derived permeability data from extensive in-house database by Hydrolex, and this diagram, which I will not go into, just illustrates the detailed pump information we have on more than 37 boreholes. All this came together in a three-dimensional model which represents all the data I've described in a single three-dimensional computer-based model, which is then input into the numerical analysis in the standard ModFlow package, which is the industry standard for such work. At this time, Hume Coal have not provided a mine layout, but a pre-feasibility study indicated a target of about 4.1 million tonnes of coal per year. From this, it is possible to calculate that the mine area will grow by between 1.2 and 2.9 square kilometres per year. Hume have also indicated that the mine design will limit strata cracking and subsidence. From this, we can assume that it will not comprise longwall mining, and for the purpose of the model, we have not assumed longwall mining and have calculated groundwater impacts with and without cracking of the strata above the coal. No cracking is similar to old-fashioned board and pillar mining. The model has been run for an initial mine area of 4.5 square kilometres and a final mine layout of about 45 square kilometres. This is shown in plan, where the blue area is the adopted initial mine and the 45 square kilometre is the final mining area. For the computer analysis of the groundwater impacts, we have to cut up the whole model into cells, somewhat like slicing a cake, and these cells incorporate the layers of the model. This information is then fed into the computer, and from the analyses we get the predicted drawdown of the groundwater table and the calculated inflows into the mine. We will now look at a summary of the results of those calculations, and we'll first look at depressurization, which is separate from groundwater inflow. In looking at depressurization, we will first consider the small 4.5 square kilometre mine that may represent about 3 to 5 years of mining. We'll look first at the drawdown in the lower Hawkesbury sandstone aquifer, and to remind you of this, I'll go back to one of the bore pump data logs, where we can see the blue zones just above the Wongawilli zone, which are highly productive groundwater zones. The drawdown in this lower aquifer after about 1 year is shown in these contours, and the red bullseye represents drawdown of greater than 80 metres after 1 year, directly above the mine. After 2 years, the bullseye has expanded, the amount of drawdown has increased to 100 metres, and it now encompasses an area much greater than the 4.5 square kilometres of mining. We can continue to track the depressurization, and after 5 years, the bullseye, the red bullseye where the drawdown is greater than 100 metres, is now larger than the area of mining and is a significant proportion of the whole exploration area. If we now look at the possible 45 square kilometre final mine, then after 10 years we find that the dark red contours, which represent significant drawdown, encompass almost the whole exploration area. And above the centre of the mine, the drawdown is about 160 metres in the lower aquifer, and if we look at the upper aquifer in the Hawkesbury sandstone, we find that the drawdown is about 140 metres, and within the whole of the exploration area, the drawdown is greater than 100 metres. This means that bores in that area would mostly run dry. In cross-section through the model, if we look at the dark red zones, which represent substantial drawdown, we can see that they extend both in the north-south and the east-west section from the coal seam through to the ground surface. In addition to considering drawdown of boreholes and drying of boreholes, it is worth looking at Medway Dam, which is just to the northwest of the Phase 3 drilling area. We can gain some idea of the possible impact on Medway Dam by looking at the predicted drawdown in that area. The computed change in total head beneath Medway Dam is between 100 and 120 metres, which one would expect would have a significant impact on the dam and its feeding streams. Now we need to look about inflow volumes, predicted inflow volumes into the mine. First we will look at the initial 4.5 square kilometres, and we have calculated the inflows using our best guess permeability values, but also upper bound and lower bound values, because we don't know these values precisely. Our best estimate is an inflow of about 18 megalitres per day, which is about 7 Olympic swimming pools per day. For the 45 square kilometres, we've done the same calculation, again an upper bound, lower bound and best estimate, and we calculate an inflow of probably about 40 million litres per day. So our best guess estimate is a mine inflow of about 16 Olympic swimming pools per day, or 40 megalitres per day, plus or minus 50%. For comparison of other mines in the southern coalfield, Tahmoor, the wettest of them, is only 4 million litres per day. And the reason why Sutton Forest is expected to be much wetter relates to the different geology and the absence of low permeability strata over the coal in the southern highlands. For a completely independent health check of our computer calculations, we have considered the Berrima Colliery, which has been in operation for 85 years. This is a small colliery, and to remind you of its location, I take you back to one of our earlier plans where you can see that the Berrima Colliery is just north of the northern boundary of our model. The colliery is an old board and pillar mining with no longwall panels but some pillar extraction. It is a fact that there's been complete drawdown of the water table above the Berrima colliery. This is shown in the following cross-section provided by the owners of the colliery, Boral. In this cross-section they show the blue water table being drawn down to the coal seam level within the mine area, and we can zoom in onto this mine area and see that Boral show complete drawdown of the water table above the mine. This is shown even more graphically by a plan provided by Boral that contours the drawdown in boreholes around the colliery. The blue area is where there has been complete depressurization of the Hawkesbury sandstone that overlies the coal in exactly the same way as at Hume, and that extends far beyond just the perimeter of the workings. This drawdown may be best understood physically by considering a borehole that is directly above the colliery with one that is away to the east. The Eagle Rock borehole directly above the colliery is now completely dry, contains no water at all, whereas a similar borehole to the east at Rosedale has the water level close to the surface, so we have had more than 100 metres drawdown above the Berrima colliery. If we look at the inflow into the colliery, it's averaged 2.6 megalitres per day up to 6.5 megalitres per day. If we ratio these actual measurements up by mine area and depth, we compute 25 to 50 megalitres per day, which encompasses the 40 megalitres per day computed by the groundwater model. We now reach the conclusions to the study, and here we summarise the key conclusions from the groundwater computations. These are not opinion conclusions, they are the results of the process that has been described in this presentation. The calculations show that most bores in the Hawkesbury sandstone above and well beyond the mine will run dry. Their yields will be lost and the valuable aquifer resource will be no more. Arising from the unique geology, computed mine inflows of about 40 million litres per day are 10 times higher than the typical mines of the southern coalfields. This 40 megalitres per day inflow would severely damage an already at-risk valuable groundwater resource within the Hawkesbury sandstone. And this will probably have impact on the Medway Dam water supply scheme. These conclusions are not sensitive to mine size, mining method, and the mine duration. Finally, we would emphasise that in the Southern Highlands we have the unique opportunity to calibrate a computer model against actual historical records in a colliery which is an excellent simulation of what may occur in the Hume exploration area, and the computer predictions are completely consistent with the experience at Berrima Colliery.